Obviously, these all go hand in glove. You cannot be world-class in safety without being world-class in teamwork, and you can't be world-class in teamwork without world-class leadership. So we'll hit on all of these metrics as I go through the program. The way I want to kick off the program is to bring you along vicariously on a space shuttle launch. So for the next few minutes, I want everybody to suspend disbelief, pretend that we're all astronauts. We're going to ride a space shuttle into orbit. Rest in our pressure suits, and then around 3 hours before liftoff, we'll walk from the crew quarters, climb into the crew van, drive to the launch pad, take the elevator to the cockpit level, exit that, walk across the access arm into toward the cockpit. And I'll tell you, when you're making that walk, you're going to feel every beat of your heart in your throat. It'll be choking you. We get dressed in our harnesses, crawl into the cockpit. Technicians will strap us to the vehicle. They'll close the hatch. The access arm will be retracted, and we will be left alone. And while we're awaiting launch, we're going to be in the grips of two fundamental emotions, one of which is fear, gut fear. You will fear for your life while you're out there, but at the same time that fear is on you, you're going to be boundlessly joyful, because for most astronauts, it truly is a lifetime quest to make this flight, and with that at hand, we're going to be overwhelmed with joy. Okay, at T-minus 6 seconds, the 3 liquid engines come to life. They are checked by computers. Assuming they pass all of their checks at T0, the hold-down bolts blow, the solid rocket boosters ignite, and we're slapped into our seats with a force of about 2 times gravity, 2 Gs, as the rocket leaps from the launch pad. Now, for the first 2 minutes, it's a very rocky, noisy ride, a lot of shock waves forming on the vehicle. You're getting rocked around, these boosters next to you roaring away, so a lot of noise and shaking. That continues for about 2 minutes and 12 seconds and then ends with the separation of the boosters. At that point, you hear a loud bang. You see a whip of fire across the windscreens as these boosters were pyrotechnically separated. And now we continue into space on the 3 liquid-fueled engines, but from here on up, it was glass, smooth, and quiet. Not a ripple of noise, not a ripple of vibration. The only way you could tell you're moving, besides looking at your instruments, were the G-forces slowly rising in your body, and those would ultimately stabilize at 3 Gs, 3 times the force of gravity. 8.5 minutes up, the autopilot shut off the engines. The gas tank was empty. It was jettisoned to burn up in the atmosphere like a giant meteor. And the only thing remaining now headed to orbit was the winged vehicle. We called that the orbiter. And now we're on our way to the International Space Station, where we're going to have the great good fortune of rendezvousing with the true heroes of America's space program, Sandra Bullock and George Clooney. They got up there before we did. Okay, I wanted to share that narrative with you to set you up for this question. If we had not been pretending, if this had been for real, if all of you truly had been tied to 4 million pounds of propellant, what type of a team would you want out there holding your life in their palm? Clearly, in situations like this, where your life is on the line, and hey, I just described the everyday work environment for you folks, a team that is world-class in safety behind you. And teams get to be world-class in safety when every single team member is living safety values. And there's a lot of safety values out there, but there are 5 that I want to discuss with you in this program, because I think they have overarching importance to the success and safety of all teams everywhere. One of which is taking each other's backs, to guard ourselves collectively, everybody watching out for each other. Another is guarding against normalization of deviance. I'll define that term here momentarily. Another is owning our responsibilities, because in the end, we're going to be accountable, and we want to be accountable to the good. And finally, we all want to be engaged in a process of continuous self-improvement, certainly with teamwork, leadership, and safety, but frankly, all personal and professional metrics. Some time now on this very important value right here, and that is guarding against normalization of deviance. That's a term some of you probably are familiar with, but just in case you aren't, I'll give you a definition. I first read about this in Diane Vaughan's excellent book about the Challenger tragedy. But basically, it's repeatedly deviating from safety best practices until that behavior becomes your new normal or the collective team's new normal. I could do something here, step over a red line, safety best practice, and save some time. And so when the person does that and gets away with it, that's lodged in their brain that a risk they previously have been taught is absolute. This is a red line. You don't step over it. They realize now, well, hold on, I did step over it. I can manage that risk. It's not absolute. I just proved that. And so they're going to be emboldened to do it again and again and again until that process becomes normalized into their behavior. But however you get there, whatever pressure is pushing you into stepping across these risk red lines, shortcutting safety best practices, this is what you're going to find at the end of the road, a predictable surprise. And in the world of hazardous environments, we know what that is, your worst nightmare. It can be injuries, fatalities, environmental disasters, invasive regulatory reviews, audits, lawsuits, everything that keeps you awake at night can come about because of normalizing deviance to the point you confront a predictable surprise. And of course, what you're seeing here in this photo is the Challenger tragedy back in 1986. It is a graphic and vivid example of the process of what a process of normalization of deviance can do, because what you're seeing right here was a predictable surprise. So I'm going to tell you the story of Challenger so we can derive some lessons from that story to better protect ourselves from being victimized by this very dangerous phenomenon. Challenger was a result of the failure of the right-hand solid rocket booster. Look at the size of these things. They were 150 feet long, 12 feet in diameter, and each of them weighed 1.3 million pounds. You cannot, these things are built by Morton Thiokol in Utah and launched 2,000 miles away in Florida. You cannot transport an object this large as a single piece across North America. So these things are made in 4 propellant-filled pieces that were shipped separately by rail from the Thiokol plant in Utah down to the vertical assembly building at Cape Kennedy. There, these segments were stacked on top of each other and bolted together to form twin towers of boosters. And then you had this whole stack, we call it, was taken out to the launch pad. Now, when these things ignited, they burned at 5,000 degrees Fahrenheit and at about 1,000 psi. Steel boils at 5,000 degrees. So you had to ensure in the design that the steel of the booster was never touched by the fire that contained. So there was insulating material that ran the inside length of these segments. Now, the obvious weak point in this design is where you bolted these segments together, because there you have a potential leak path for the gas to pass to the outside, melt the steel, and cause a catastrophe. Now, I'm not going to go into the engineering specifics of the joint design that was intended to prevent such gas leakage, other than to say it was based on a redundant flexible O-ring scheme. 2 flexible O-rings, 12 feet in diameter, sat in grooves at the perimeter of each of these segment joints to form a redundant steel-to-steel pressure seal. For those of you unfamiliar with O-rings, I suspect most of you are, but for those unfamiliar, you have O-rings in your plumbing serving a similar purpose as was the O-rings on the solid rocket booster, in the sense that the O-rings in your plumbing is forming a steel-to-steel pressure seal to prevent water leakage. Same principle as was used on the booster's steel-to-steel pressure seal to prevent that hot gas from leaking out. On Challenger, both O-rings failed on the bottom segment of the right side solid rocket booster at ignition. Look in that yellow circled area, you'll see that black smoke. That's the vaporized O-rings being shoved out that bottom joint. You now have 5,000 degrees eating into that outer wall. As the rocket flies higher, the gas is vaporizing a bigger and bigger hole in the side of the booster rocket. 73 seconds up, the rocket comes apart, killing the 7 astronauts. Now, most people seeing this will immediately refer to it as an accident. Challenger was no accident, folks. Challenger was a predictable surprise. And I can say that because in this business, it doesn't get any better than to get the piece back and see how it performed. And that was the case with these solid rocket boosters. They were not throwaway items. 25 miles up, they burned out, they were jettisoned, they had these gigantic parachutes. The operative word in this recovery process is inspected. And on 12 of 24 missions before Challenger, Challenger was number 25. On 12 of 24 missions before Challenger, beginning with the recovery of the boosters from Flight 2, quality assurance and safety people at Thiokol noted that these O-rings were not performing as expected. They were experiencing very serious deviances, including burned O-rings. And these engineers grew gravely concerned about their repeated findings with these burned O-rings. Moving closer to Challenger, they began to document their concerns in very shrill, graphic language. And here is an excerpt from a memo written by a Thiokol rocket engineer 6 months before Challenger. Mr. Roger Bougielet wrote this memo, and he wrote a very prophetic sentence in that memo, and here it is. It is my very real fear if we do not take immediate action to solve the O-ring problem, we stand in jeopardy of losing a flight, a crew, and all the launch pad facilities. Mr. Bougela's prediction was only off 73 seconds. He thought the rocket was, in every sense of these words, it was a predictable surprise. Now, what was the go-to source document? Hey, what you're saying here, the risk red line is this component cannot fail. O-rings cannot show any damage. It's intolerable because if they fail, it's death to the astronauts and loss of the vehicle. So the safety best practice attached to any criticality one component is what? Hey, the safety best practice, any hint that this thing might fail, it means flight suspension. Stop. Give the engineers time to fix the problem. But for 4 years and 23 missions, 12 of which showed serious O-ring deviances, we went from Flight 2, the near miss on Flight 2, to the catastrophe on Flight 25, the identical failure mode. You have to ask yourself, how is that possible? Well, folks, when you're under intense schedule pressures, strange things can happen in the human brain. And NASA was under immense schedule pressure in the form of launch schedule pressures. Let me give you some background here to show you where these pressures came from. In 1972, President Nixon and NASA introduced the space shuttle to the American public, promising that it would be reliable and versatile, replace all present launch vehicles, and most significantly, reduce the cost to the taxpayer to 1/10 of the systems, the rocket systems we currently had at that time. It was going to be a game changer for the American taxpayer. It's going to save a bundle of money. So cheap to operate. It would sustain a launch rate of about a mission every 2 weeks, 24 missions a year flight rate. That was the goal that had to be achieved, and it had to be achieved rapidly with the shuttle coming out of the gate, because it did not make any economic sense. It did not reduce the cost to the taxpayer if it wasn't flying at that flight rate. Land on a runway, be turned to launch again. But in the process of that turn, it was taking huge amounts of resources and a great many more weeks and months than anybody ever anticipated to get the mission turned. And so we were falling further and further behind with this launch rate. And the drumbeat grew louder and louder. We have to turn these things faster, get them up there quicker to meet that goal of a mission every 2 weeks. And you can see how this was playing out with a contractor. This is the Rogers Commission investigated the Challenger tragedy, and here's some contractor testimony. The problem was the increasing launch rate. We were just getting buried under all this stuff. The system was about to come down under its own weight. Here's a comment by the House committee that investigated the Challenger disaster. NASA's drive to achieve a launch schedule of 24 flights per year created pressure throughout the agency that directly contributed to unsafe launch operations. You've been in this exact same situation. You're on a team that's under intense schedule pressure. You're facing a threat to that schedule. What to do? And NASA, of course, was facing it in the form of that O-ring problem. What you should do is what you said you were going to do. I think teams are very, very good at defining teams that operate in hazardous environments are very good at defining those risk red lines. It's when they're being pushed on schedule pressures and they're bumping up against that risk red line. What do? You stop. You stop. You invoke the safety best practice. You stop. In our case, it would have been flight suspension. For you, it's stop work. Give people time to figure out what the problem is. But too often, that does not happen. You can look out there at the great tragedies that have occurred, Deepwater Horizon, some of these other ones that are out there. They had the risk red lines. It's well defined. It's just that under schedule pressure, they decided to take that step across that risk red line. Accept deviances from safety best practices to maintain schedule, budget, things like that. NASA dynamics of what's causing the occasional burned O-rings, and they conclude that damage will never be catastrophic. And so what you're seeing here, folks, is slowly, flight after flight, year after year, what's happening. O-ring damage is becoming expected. And this is not hyperbole, folks, not an exaggeration to say this. I want you to look at this recommendation by the contractor to a NASA manager after seeing damage earlier in a concerned Flight 11. The recommendation was to fly the 11th mission, except in the possibility of some O-ring erosion due to hot gas impingement. O-ring damage is becoming expected. Diane Vaughn, in her book, made this statement. Between 1981 and 1984, 4 times an incident that was first seen as a deviant event was reinterpreted as non-deviant. So we've gone now from O-ring damage is intolerable to O-ring damage can be expected. And you can see why that happened is because each time that risk red line, that risk ceiling formed by that risk analysis document, each time that was breached, it chipped away at it until what? It was no longer there and had been replaced with this paradigm right here, that all future risk justification is being based on the experience base, past success with risk taking. And that, when you reach that point, folks, you are absolutely in the grip of normalization of deviance. When you start basing risk-taking on your success with past risk-taking, no question about it, you're in the grips and the vice of normalization of deviance. And by the way, there are a couple other things that loom large in the story of Challenger, and let me clue them forward. So I want you to think now, as we're summarizing the situation that was existing on the eve of Challenger. You have a team that has normalized a dangerous safety issue, the burned O-rings. They've had a planned reduction in safety oversight, and there's a communication failure, a very serious communication failure. So no team is going to survive even one of these, much less experiencing all 3 simultaneously. And of course, we found our predictable surprise with Challenger. And I want you to consider the costs of what you see here in this photo. 7 families irrevocably destroyed. A lifetime of agony for those who were closest to the flawed decision-making. I don't think many people think about that. How many people do you think out there would, were just basically their lives ended with knowing that they had participated in some flawed decision-making to bring about this? Billions in program losses. It took $2.5 billion. It took 2.5 years and billions of dollars to redesign that booster. National security was jeopardized because we couldn't launch some secret satellites for the Air Force because the shuttle was grounded, and they'd been designed to be launched by the shuttle. And of course, NASA's glorious Apollo reputation was vaporized by Challenger. And why? Why did it happen? Right here, in a sentence. Team failure to comply with established safety best practices. They, as many teams do, and operate in hazardous environments, had well documented the risk red lines. It's just that they got stepped over at once. It became easier and easier until that became the norm. And it's a very dangerous phenomenon here. So what do we learn from the Challenger disaster?